Okay, so just logistic update. You should be working on your projects. Talk to your TAs if you have any questions about your projects, right? I think everyone should know who the TAs are. And if you have any questions, feel free to talk to your TAs, okay? So they have office hours and such, so don't delay. I think that hopefully by the end of the week, we'll try to get some feedback on your projects, but at the same time, again, if you have any questions, talk to the TAs. That's the best. Don't be passive, okay? So keep pushing on it. Okay, so today what I'd like to do is I'd like to talk about representation learning for reading comprehension. This is kind of a very interesting topic as a combination of deep learning and natural language processing. Okay, so I'd like to kind of show you some research that's taking place in that area. And some of these slides I actually borrowed from Buan's talk. Okay. Let me show you what the problem is. It's pretty exciting and actually pretty challenging. So imagine that I give you a document. Think of it as a CNN news story. All right? It says, arrested Illinois Governor Rob Blagojevich and his chief of staff John Harris on corruption charges, so forth. Included Blagojevich allegedly conspiring to trade the Senate seat left vacant by President Barack Obama. So I don't know, like in 2008, there was a big scandal where Rob Blagojevich he was using corruption and was trying to sell Obama's Senate seat in the Senate. So was trying to get somebody to replace basically Obama, which is kind of made a lot of news. And imagine now I'll give you a query. And query says, President-elect Barack Obama, Senate user, he's not aware of alleged corruption by X, who was arrested and so forth, right? Now the question is, who is X? And you can see that if you look at those two sentences, you have to understand that Rob Blagojevich is Illinois governor, and then he was conspiring to sell Obama's seat, right? So in order to answer this point, what X is, you kind of have to look through the document and get a couple of sentences at least in different parts of the document to get to the answer, right? And also the answer is Rob Blagojevich. There's a very interesting data set, who did what data set. You basically try to figure out what the answer should be, right? So obviously this is not an easy task in general. People can solve it fairly accurately, but for machines it's quite difficult, right? Because the answer here could be Barack Obama, it could be Rob Blagojevich, or it could be John Harris, right? Because all of these names are popping up. So if you just blindly look for names, it's going to be very difficult for you to answer that question. So we're going to form the task as follows. Given a document query pair, so I give you a document, right, and I give you a question. I want to be able to find the answer, and the answer is going to be in some, answer is going to be an answer to the query, but the answer is going to be in some predefined set of possible answers, okay? So generally, the answer is going to be coming from a fixed vocabulary A. So I give you that vocabulary a priori. This is sometimes easier to, so you think of it as a classification problem, right? Given a document, given the query, I want to classify. And typically you have maybe 2,000 possible classes, so you want to find the right class. Sometimes it's just set up this way because it's easier to validate and compute, because then you can look at the classification accuracy. There is also another class of where A might consist of all tokens, or span of tokens in a document. This is sometimes called extractive question answering, which is sort of goes beyond classification, which is basically to say that in this document, find me all the tokens that can answer that particular query, right? Or I can give you some span of tokens in a document. So I can tell you like sentence 1 is the answer to the question that you're asking, or sentence 5 and sentence 6 are the answers to the questions that you're asking, right? So this is a little bit more elaborate because you have to find which span is answering that question, but it's also a little bit more relevant, particularly if you want to answer the question correctly. So this is actually a good test for text representation, right? How do we represent the text? And we've talked a little bit about language model. In fact, for your third assignment, you've built a very simple language model, right? A lot of work is happening on how can we get the better representation of the textual data so that we can, be able to answer questions correctly. Okay? Okay, so what's the approach? We're going to look at the supervised learning approach, right? We have D. Think of it as a collection of, a Wikipedia page or Wikipedia pages or a document or CNN news story. We have a question, and we have an answer, and we have n basically data points. We have a model. What we're going to do is we're going to try to predict the probability of, or try to compute the probability of the correct answer given the document and the query, right? So we're going to try to predict probability of correct class, where class is some predefined set of possible answers. So it's a classification problem. And the loss is going to be the log loss, right? Your standard classification, if you're doing classification, is going to be cross-entropy loss, which is to say, what's the log probability? You're trying to minimize the negative log probability of predicting the correct answer given the query and the document. And the training basically comes down to minimizing this loss, right? Standard setup, right? This is exactly what you would do if you were to classify MNIST digits, right? Or classify whatever things on the ImageNet. No different, except for the input here is the textual input or sequential input. So what we're going to focus on is we're not going to be focusing on training or defining different loss functions, but we're going to be focusing on the models, okay? So what biases, what architectural biases can we build into the model? So a lot of work is actually happening on the modeling aspect, right? Can you come up with a better representation, better model, so you can be able to answer those questions correctly? And as you can see, this is not a simple task. It's actually a pretty complex task, right? Being able to read coherently the whole document, being able to answer, and then the question comes in some natural language. So I have to be able to understand what the question is asking to be able to provide the answer. So architectural biases. So one architectural bias is the designing some architecture of the neural network, right? So for example, if you look at convolutional neural networks, they're geared toward images, right? Because you can use convolution. If you look at recurrent neural networks, we've seen in a couple of our classes, these are biased towards processing sequential data, right? We've seen that. For reading comprehension tasks, what biases could we build to reflect linguistic phenomena, right? And typically, we're going to be interested in three things. We're going to be interested in alignment, right? If my question is asking about, something about corruption charges and something about President-elect Barack Obama, I should be able to somehow take that information and find the relevant pieces in my document, right? Because that's what we would do. Paraphrasing, that's obviously common. You don't want to do exact matches. If there are paraphrases, we want to take care of that. And then aggregation. Aggregation, typically, it's an inductive bias that you can put in the model. It basically says, well, if I have a document, and this document mentions President-elect Barack Obama 300 times, then maybe no matter what the question you're asking me about, the answer is going to be President-elect Barack Obama, right? So that's an architectural bias. I mean, this is typically the aggregation bias. You're kind of trying to figure out, what is this document talking about? And the more mentions you have of a particular name or a particular noun or a particular entity, probably you're going to be asking questions about that particular entity. So this is going to be part one. And then if we have some time, I'll show you some examples of incorporating syntactic and semantic dependencies into the model. This is a little bit more on the advanced side. Okay, so let's come back to this this particular setting. The alignment would basically do the following, right? It will say, well, if I'm looking President-elect Barack Obama and there's a President-elect Barack Obama, so maybe there's somehow relevance between the two, right? If I talk about corruption, corruption happens there. If I talk about Senate seat is picking up there, right? So there's some alignment that you might want to do, right? Obviously, that's the first thing that any information extraction system would do, right? There is also paraphrasing. Like if you look at corruption, so conspiring to sell versus trying to sell, right? Those two things kind of mean the same thing. Or if you looked at the alleged corruption charges, that's similar. Obama's seat, Senate seat left vacant by President-elect Barack Obama, and those two things also mean the same thing, right? So you want to take paraphrasing into account as well. And then aggregation, you know, it's kind of where you look at the entire document and you're trying to come up with sentences or with representation that's relevant to the query, okay? And how you exactly doing this, alignment, paraphrasing, aggregation is what you build into the architecture of the model. Okay, so paraphrasing. How do we do paraphrasing? Well, you've seen from your third assignment is what you can do is you can use word vectors and you can use RNNs to represent document and query, right? So paraphrasing is actually an interesting one because if you're using word vectors or some extensions of the word vectors, then you can kind of like say, well, cats are similar to dogs, right? So if I'm paraphrasing one to another, that should be reflected in the word vector. So that should be reflected in the RNN architecture of the model. Alignment is an interesting one, and there's something that's called multiplicative attention, and I'm going to talk about, which allows you to come up with some alignment between what the query is asking and what you have in the document. And aggregation, typically aggregation is happening where you have multiple passes over the document. So it's almost like you're reading document multiple times, filtering out irrelevant information. And there is something that's called point-to-sum attention mechanism, which is just a very simple way of aggregating information over the entire document. So we're going to primarily focus on these two. Okay? So representing documents. We've talked about this. How do we represent the documents? Well, the first thing is we're going to look at the representation of documents, which is composition of word vectors, right? And in fact, in your third assignment, hopefully you've learned what this representation should be using a simple neural language model, right? For the brave ones who've actually tried using RNNs and some packages, you could probably see that you can actually learn pretty reasonable representation of the words, right? So words are being mapped into these vectors. And so now things that help in general when you're doing this mapping is pre-trained glove embeddings work fairly well. Typically for these kinds of tasks, they work a little bit better than word-to-vec embeddings. So for those of you who are not familiar with glove embeddings, it's kind of a slightly different version of word-to-vec embeddings. You can look at the papers if you're interested in it. Random vectors for out-of-vocabulary tokens at test time, it's better than trained with unknown embedding, right? So think of it this way. When you were doing your third homework, if you ever encountered a word that was not in your vocabulary, you just put it into the token that's called unknown, right? And you're just predicting this unknown thing, right? What happens in these reading comprehension tasks is that if at the test time I give you a document and I give you a query, and a document and query is asking about like some name that you've never heard of before, right? Typically what's better to do is it's better to assign a random vector to this unknown token, right? The reason why is because you're interested in doing matching at test time, right? If I give you a query and I have this unknown vector, the way that we do it is we say, well, this is very weird last name, but this last name appears here and here. So you can match the two and figure out how to answer the question, right? Same thing happens here. If you assign a random vector to out-of-vocabulary token, you can actually do much better, as opposed to say, well, that's actually something that I call unknown. and just learn a word embedding for the unknown vector. Because if you have multiple unknown vectors and at your test time, then you're just going to mess up. It's like pushing everything into one bucket is not reasonable. Character embeddings is also helping. So in many cases, if you have misspellings or you have phonetic relations, you can incorporate character level embeddings as well, right? Character level embeddings has been some work where people have shown that if you actually use RNNs that basically read one character at a time, and then you get the representation of the word by combining all these character level hidden states, then in some cases that can help as well. Particularly it can help with if you are with misspelling mistakes, or sometimes, you know, if there's sort of derivatives of different words, then character-based embeddings, they can learn meaningful morphological features. Okay, so now, how do we process documents in query? Well, we're going to be using bidirectional GRUs to process the tokens, right? These are just bidirectional recurrent neural networks with special mechanisms. We've talked about those. It's a simplified version of LSTMs. But the idea here is, again, you have a forward GRU, right, that reads the document from left to right. You have a backward GRU. And then you're concatenating both of these representations to get your feature vector, right? That's the embedding of this will represent the embeddings of the document and the query, right? So you're concatenating both of them, the forward and the backward, right? So you can think about this as, why do you do forward and backward? If I look at the word governor, right, and I look at this particular hidden state, think of this hidden state as kind of embedding of the word governor plus some context around it, right? Because this RNN will basically say, well, it's arrested Illinois governor, and this one will say it's Blagojevich robbed governor. So now when you look at the embedding of the word governor effectively, you're sort of embedding some local context around it, okay? So this representation of the hidden state here, the governor, will kind of mean it's really arrested Illinois governor Rob Blagojevich. That's kind of, you can view it as a representation of this particular token, right? And now you basically say, well, what I'm going to do is I'm going to represent my document this way. I'm also going to represent my query the exact same way, okay? Now, obviously, your document could be very long, right? And that's where computations are taking time, because if your document is very long, you're basically running this RNN over the entire document forward and backward. And intuitively, you can say each hidden state here looks at some local context and incorporates that. Okay? Same thing for the query. Okay, so now, and obviously they're in different lengths, right? The query could be, you know, a sentence or 2 sentences. A document could be 1,000 sentences, right? So now what we're going to do is we're going to look at something that's called gated attention mechanisms. And a lot of work's been done in terms of figuring out what's the right attention, what's the right alignment to do, right? So let's look at what the attention does. For each token in D, right? So here's Blagojevich. This is word-to-vec embedding. This is the representation after incorporating the context around it. And this is the query. So this is what we're going to call D sub I, and this is what I'm going to call Q sub J. What we're going to do is we're going to compute these softmax weights, right? So what we're going to do is we're going to take DI, this vector, and look at the cosine similarity, or look at the dot product with every single vector here, right? And then we're going to exponentiate and normalize. So alpha I j's will give me the probabilities that sum up to 1 of relationship between this representation and this representation, this representation, this representation, and so forth. So you can think of it as an alignment. It really is saying, if I look at Blagojevich, probably it's incorporated Illinois arrested Governor Blagojevich in something like Senate seat. That's going to be representation here. Maybe it will have high dot product with corruption, right? But maybe it will have low dot product who was, right? So now if you look at this particular dot product, it will pick up that Blagojevich with corruption, they might have high sort of probability. I mean, they might be vectors when you do the dot product, it will have high value. So if you normalize, it will have higher probability. So now I'm going to represent token-specific representation of the query Q sub I is just the weighted average of these representations, right? So intuitively, what this attention is doing, what it's doing is it's saying for each token and document, which words in the query are most relevant to this particular token in a document, right? So it will pick up the most relevant ones, and then you take the weighted average, right? This is exactly what attention mechanism would do. But you're doing attention over tokens in a query. That's something, again, sometimes you can think of it as a soft alignment. You're aligning each word in a document to what's being asked in a query. And then what you can do is you can use element-wise multiplication to gate the interactions between the document tokens and query tokens. And that's important. This gating mechanism, this is element-wise multiplication, gives you the representation of how much this particular representation matching up with the representation that you see in a query, right? Sometimes people look at just adding the two or concatenating the two. Gating works much better. So now you have a new representation of this token D. Okay? So what is this operation doing? This operation is essentially finding features in the query that match the contextual representation of the document, right? So for each token in the document, you have some contextual representation, and you're finding matches in the query. And you're doing it in soft way, which basically means that you can backpropagate through this operation. That's important, right? Unlike in traditional retrieval tasks, right? You can just do matching. You can say, well, corruption happens in a document, well, it happens in the query, there is a match, maybe I can do something about it. This one is actually doing both paraphrasing as well as matching in a soft way. And all of these operations are differentiable operations. So you can backpropagate through them in order to update the parameters of the model. And then you're gating the document representation by multiplying it with these features, right? So you find these contextual features, and then you're gating it with the token of the document. Now, you can also you can do multiple hop representation. And what this will do is it will help the model to combine evidence from multiple sentences, right? Because this gating mechanism will effectively, like if there is no relevance, if this guy is not related, this particular word has no relationship to any of the words in the query, then what's going to happen is that this thing is going to be mostly uniform. And then typically these gates will have small values. So the representation here is going to be not that large in general. And so what goes up to the next level, the model will learn to kind of ignore relevant information. So this kind of pass, you can think of it as a filtration that basically gets rid of irrelevant information, and the relevant information is propagating up, right? And so you repeat it for k layers, right? So it's kind of nice. It's a soft way of picking up important information, getting rid of not important information, and you do it in the next level, you aggregate more information, and again, you do the same procedure and so forth. Okay? So that allows you to also look at the potentially combine multiple representation coming from multiple sentences. And this is the overall architecture, right? So you kind of look at, given a document, you do the embeddings, you do the ByGRU, you do the gating, and you repeat it for k layers. And then you go through some softmax and some aggregation procedure, and then you predict the probability of the answer. So it's a classification model. It's also interesting to look at this particular architecture and say, well, a lot of work, 3 or 4 years ago, think of this as being a convolutional neural network, right? You have some input, you do some convolution, you do fully connected layers, and so forth. Now these models are becoming much more elaborate, where each layer is some recurrent neural network that's gating, that's processing sequential data, right? And then gets passed to the next layer and gets processing the sequential data. So the architectures are now becoming much more elaborate, right? And the surprising thing is that these models do give you state-of-the-art in terms of predictive accuracy, being able to answer the questions correctly, which I think is pretty interesting, right? So these architectures are no longer, simple ones, like do a bunch of convolutions, do a bunch of fully connected layers, and then classify. They actually now sort of recurrent neural networks sitting inside of a multi-layer neural net. The other thing that I want to point out is that this entire system is differentiable. And as I mentioned before, your goal is to predict the probability of the correct class. So you can use softmax, or you can use any other loss functions, whatever suitable loss function for your task is. But the important thing is that you can backpropagate through this entire model all the way to the input. In principle, you could learn the word embeddings for your task if you have enough data. You could learn, parameters of the GRU. You could learn parameters of the attention mechanism and so forth, right? So at the end of the day, it's an end-to-end system that just looks at the raw textual data, looks at the query, again, textual query, and just does the whole thing, right, jointly. So there is no sort of manual preprocessing or manual operations that you're doing here, right? Which is pretty cool, I think. So output model, what's the output model? The output model is actually pretty simple. The probability that the particular token in the document answers the query, you're just basically taking the inner product between the query embeddings and the output of the last layer, right? So at the end of the day, you're just doing simple element-wise dot product, and you're just doing softmax, right? Over possible answers. Now, the key thing is the aggregation, which is paper was by pointer sum networks, is the probability of a particular candidate C is aggregated over all document tokens which appear in C, right? So you're aggregating. So basically what that means is the token Obama appears a lot of times, then its probability is increased, right? Because you're aggregating these things. And that's going to be, so you're getting the scores for each mention at the output layer, and then you're just summing them up. So the more mentions appear, the more probable it is, right? So that's a bias that's incorporated into these models. But obviously, again, the entire system is differentiable, so the model can learn to either give it a high score or give it a low score and so forth, right? The word "the" would appear a lot of times, right, in the document. But that wouldn't be the answer, so generally you would push the score of it down. And then you're basically picking the candidate with the maximum probability selected as the predicted answer, right? So given this particular model, you just look at the one with the highest probability. So you're just solving classification problem here. And then you're using cross entropy to basically train the model. It's a standard classification problem. So there's a lot of work that people are looking at these models, and again, they are a little bit constrained because it is a classification model, right? You only have to choose one of k answers, but at the same time, people are using these kinds of tasks. They try to form reading comprehension as a classification task because it's easy to measure performance. Like, did you get the answer right or not, right? Here is an example of a whole bunch of different data sets. There is CNN news data set, there is Daily Mail, there is children's books, and who did what, and a bunch of different data sets. And if you just look at the word embeddings, this is just the word embeddings, they don't do so well by themselves, right? You can obviously just sum the word embeddings, try to do some matching, and do the classification. If you're using RNNs like GRUs or LSTMs, the performance goes up. But if you take and you use the gated attention, then you get performance improvement. And then there's something called gated attention plus some features. So there's some extra features you can add to the system. Like, is this word appearing in a document? Like, if I'm asking in the query, if I'm asking a specific thing about some entity, if this entity appears in a document, I add additional feature, right? So this is not as important a feature, but I wanted to point out that, you know, the attention piece, the gating attention piece, is actually helping you across all of these different data sets. And I think that on 4 out of 5, it's basically state of the art right now. Here's an example of what I wanted to show you, like a whole bunch of different approaches, right? So there has been, in the last 3 or 4 years, you can see that, you know, there's a whole bunch of different papers. People are studying architectures, people are studying different attention mechanisms, people are studying, you know, how do you do multiple passes through the data and so forth, right? So you can see there's a lot of work on, you know, in this space, and as the time progresses, people are getting better and better results, right? Which is what you'd expect to have. Mind you that we're sitting at, like, you know, 77, 80% accuracy, and people are at like 99. Right, so people are very good at looking at the document. You ask me the question, I can reason about it, and I can answer the question, right? So there is a little bit of, people are trying to figure out how can you actually do reasoning. Because sometimes for many equations, particularly for this data set, no, the who did what data set, it's not shown here. But for this data set, you actually need to kind of do a little bit of reasoning. You need to figure out what the question is asking and who's referring to what in order to be able to answer the questions. Here's an interesting thing you can do. You can look at the attention and figure out what's attention doing, right? And the attention is really, for this particular query, the attention are the softmax weights, right? So you can say if this is representation of Blagojevich, right? What's its attention in the query? What is it paying attention to, right? So you can just look at the learned similarity between the representation of Blagojevich and the representation of other words, right? So it turns out that the first layer in this particular example associates Blagojevich with alleged corruption. So there is a high attention weights. So it picks up that the representation of this word and the representation of corruption, you know, they're similar to each other. The second layer actually picks up Senate, right? So as you go through multiple layers, again, it's very hard to visualize these attention mechanisms precisely because they're all soft, right? It's not hard attention. It's not like I'm paying attention to one thing. It's a distribution of things you're looking at. But nonetheless, it's basically picking up that Blagojevich has to do with alleged corruption and has to do with Senate seat. And so now when you're answering a question about, you know, who was charged on corruption charges, the model then can assign high probability to Rob Blagojevich, right? Which is kind of cool because it somehow is able to figure out that these are the important features to look at in order to be able to answer this question correctly. Which is, again, I think kind of interesting. It's not like we're telling the system, for this question, these are the important features to look at, right? This is a setting where the system is figuring out what are the important features to look at in order to be able to answer the question correctly. There's been some work previously in the vision community where people are, you know, realize that, oh, I want to classify this image as a cat. Maybe I can first classify attributes. Right? I want to classify that it has fur, it has 4 legs, it has, you know, tail, and so forth. If I can classify all of these attributes, then I can be accurately, you know, more sure that this is a cat, for example, right? And that's a good approach if you have labeled data, because somebody has to go and collect the data, right? So imagine somebody would have to read these documents and say, Senate seat and alleged corruption are important features. So whenever you're answering this question, you need to predict that these are important features. But the system does it on its own, right? It's figuring out these are the important features to look at. And if you look at attention across, you know, a whole bunch of different documents, a lot of times these features that the model is picking up actually make a lot of sense. So summary so far, you've looked at the multiplicative attention for documents, very simple, and multiple layers allow model to focus on different aspects of the query. If you're interested in kind of playing with these models, there is code and there's data and stuff online. So you can just basically download it and use these models. The other thing that I wanted to show you quickly is this notion of words versus characters. So word level representations are very good at learning the semantics of the tokens, right? Because that's the embedding that you were learning. For example, again, on your homework, on your third homework, you were learning the embeddings of the words themselves. And character level representations are more suitable for modeling subword morphologies. Like, for example, cat and cats, right? They should be similar to each other. In word embedding space, you would have a representation for cat, you'd have a representation for cats. And you'd be treating them as completely different word embeddings, and hopefully through learning, maybe you can learn that they're similar to each other. But if you're using character level model, then by default, you can basically figure out that they are very similar. So word level representation obtained from learned lookup tables, right? Character level representation is usually obtained by applying recurrent neural networks or convolutional neural networks. There's been some work on just routing convolutions, 1D convolutions over the characters. And there's been some work on hybrid models, right, where basically you can combine word level and character level. And one commonly used method is just to concatenate the two representations. You get one representation, get another representation, you concatenate, and you go from there. But you can also do this gating mechanism again to get the representation of the hidden state. So you can say it's a character level representation. Think of it as an output of an RNN. This is a word level representation. Think of it as you have a word, you go through some embedding matrix E, you get the lookup representation of that particular word, and this is a gating. And the gating here is a number between 0 and 1, right? So you can say, well, it's almost like an attention. You can say if gating is 0, then you just use word level representation. If gating is 1, you're basically using character level representation, right? And the gating itself, the gating function itself, in this case, can be based on some external features. For example, you can use some external features like named entity tags, or partial speech tags, or document frequency vectors, or word lookup representations and such. So you can try to come up with some meta features that can tell you, should you be using characters or should you be using words? And there's been some work on trying to figure out what these things should be. It turns out actually one very useful feature is the frequency. For example, which makes sense because if you only see, I don't know, dog in your entire data set only once, it's very difficult for you to learn representation of the dog, right? But maybe you've seen dogs and other variations of dog in your training time, then the character level model would be a much better representation of it, right? Let me just skip through the examples. I mean, you can actually, once you do the combining, you can improve the accuracy. But here's an interesting thing, what you can do. So high values of the gate means it's a character level representation. Low value gates mean word level representation. So lowest basically means that for these words, the model is choosing to use word level representations. And you can see because these words are so commonly used that you have enough information to actually learn the word level embeddings, like many, then, his, this, and such, right? There is no need to use characters. But these are the words that character level model is picking up and says, I want to use character level embedding of these words, which is kind of interesting, right? Because it's like different names or different things. So based on the models basically I think the model is like figuring out that whenever you have like the gum at the end, I think it's the name of the city, right? Or if it's, I don't know. But it's basically choosing Ville, I think that's another thing. When it sees something like Ville, that also means it's a city. It's the name of the city, right? And that's the only thing you can do if you actually use it morphological aspect, if you use it at character level embeddings, right? So sometimes it can be much more useful using character level embeddings. Okay, so let me actually, in the last 20 minutes, I wanted to show you some of the linguistic knowledge as explicit memory for RNNs, where we're trying to basically incorporate some external knowledge. And that's a very big area of research. Here is a dataset called Lambda dataset. If you look at this dataset, you know, read this dataset, and then let's see whether you can solve it. So how many of you think X is Owen? Or how many of you think X is Emily? How many of you think X is Terry? Terry? You think it's Terry? Emily? Oh, come on, you can do better than that. So if you actually do it, at least the native speakers, I know that they've tested it on native speakers, people can solve this task fairly accurately. So these passages are filtered such that humans can correctly answer when given the whole context, but not when given only the last sentence. So for example, if I just give you the last sentence, she gave me a quick nod and then turned back to X, there is not information to answer the question. So they specifically constructed the data set so that you look at the entire context in order to be able to answer the question, right? So you can't cheat by saying, oh, if I just want to answer something about X, I just look at the words here, and some words appear, like Emily or Owen appears in this sentence, then I just predict that's the thing, right? So you can't do a local pattern matching, basically, right? Which is most of the deep learning models effectively are doing. They're looking at the local context, they look at the local piece, and then just classify or identify what that is. So it goes a little bit beyond just simple pattern matching, right? Now, the way that we're going to do it is we're going to construct it as a question answering or as a reading comprehension task. So the query is going to be, she gave me a quick nod and turned back to X, and X is assumed to be in a document. Okay? So it's not like some X, which is a fixed vocabulary, but it's some fixed vocabulary, but it's assumed to be in a document, right? And so the reasoning approach is performed best on this task. And again, this is the best sort of done by. So how do we solve this problem? So there is something that's called syntactic dependency, right? You can say something like she gave, right? And then she turned, and then turned back to whom? To X, right? So there's some reasoning that you can do. Maybe for those of you who are not studying natural language processing, might not be obvious, but you do it, based on this query that she gave and then she turned, right? It's not somebody else who turned, it's she turned. There's also some semantic dependency, like, as I mentioned, that she turned and then turned to X and so forth, right? But now the question is, how do you answer? Like, is it Emily? Is it Owen? Is it Terry? So one thing you can do is you can use something that's called coreference resolution, right? Which basically means that when she says her plain face, that corresponds to Emily. When she called, that's Emily. Owen, please meet Emily. Owen is the same as Owen, right? So now if you can basically identify that she is the Emily, gave me, Owen, a quick nod and turned back to X, then basically the answer becomes obvious, right? X is Terry, right? So this is kind of, this is something known co-reference resolution. It's very important because you need to understand who's referring to whom are we talking about, and such. This is just one instance. Obviously, there is a whole lot more things you can do, but this is one important thing to do, right? So architectural bias. So these co-reference mentions may be far apart, right? So it's not like, I'm talking about one thing. I can be talking about one thing, then switch to another thing, then coming back to the original thing. So the distance between mentions could be far away from each other. And the RNNs in general, they tend to forget long-term interactions. We know about this, right? If I talk about something, and then I talk about something else, and then come back to talking about the first thing, if you're just using RNNs, they tend to forget, right? They can't carry information for a long time, even though they call it long-term memory. They're really not that long-term. They're kind of shorter, a little bit better than short-term. So you can use a memory-augmented architecture. So for example, one of the things you can do is you can look at these co-references and say, well, if I have some co-references, I can augment my model with skip connections, right? So you can use these linguistic annotations to guide memory propagation in a network. So for example, here, what can you do? If I give you a sequence of sentence, Mary got the football, she went to the kitchen, she left the ball there. And now if I ask you the question, where's the ball? Right, it's very easy for you to answer, it's in the kitchen, right? But general for machines, it's very difficult to do because you have to understand that Mary got the ball, and then you have to understand that she went to the kitchen, Mary went to the kitchen, and she has the ball, right? And then she left the ball there, where? In the kitchen, right? So for us, it's obvious, right? Because just you look at the three sentences, it's no problem. For machines, it's not that easy, right? Because you have to understand that Mary and she, that's the same thing. And when she went to the kitchen, she has the ball. There's some sentence that basically said, Mary got the football, she left the football. She went to the kitchen and she picked up an apple. Where's the football? Well, it's still where it was before, right? Stuff like that. So it's obvious for us, but very difficult for machines. So there are things like co-references, there are things like syntactic dependencies, roles, and so forth, right? Like she went, or Mary, and then she, and so forth, right? So you tend to understand something about the structure here. So as before, we're going to be representing both document and query in the same way. But now we're going to be representing queries and documents in terms of the graphs. So they're going to be represented in matrices, but when we're going to have a graph representation, right? So think of this as follows. In addition to having these RNN models, we're also going to have these additional links, skip connections. So we're going to have a skip connection between Mary and she. And the reason why we want to do this is because there's some representation of Mary. That representation is going to be affecting the representation of she. Right? So when we talk about embedding of the word she, we look at the local context around it, like football, she went, she went to the kitchen, some context around it. But because we're adding these skip connections, the representation of the word Mary will also be affecting the representation of the word she. So, we can kind of almost like force it to say, intuitively force it to say that she and Mary, they kind of mean the same thing. So if I'm asking you about Mary, and Mary is going to be close to she, then I can say, well, kitchen, Mary is in the kitchen, right? So it's almost like taking all of that information and building a better context, right? It's almost like take the word Mary and put it right in front of she, basically, so that we can get a better representation, right? We can represent it using a forward DAG, right? So these are skip connections moving forward whenever we do a forward pass in the RNN. And obviously, by adding these skip connections, we can add these longer-term dependencies, right? If I say Mary is doing this, and then something else, something else, something else, and then says she came back to the kitchen, then if I add the skip connection between Mary and she, then obviously the information can propagate right from Mary to, whatever she's doing in the future. And then there's a backward pass for the bidirectional RNN. So we start from the back and also have, we have these bidirectional connections. Mary goes to she and she goes to Mary, right? And it turns out that if you look at the word, for example, went there, Then, there is a she. The representation of the she is going to be coming into this representation. And left to the kitchen is going to be going out. Right? So think of it as, again, as an architecture with a whole bunch of skip connections. And what you can think of this is you can think these additional skip connections as memories. Right? You store it, and when you get to the right part of the sentence, you can read from that memory. And you can use sort of GRU updates. You can incorporate that memory into the updates. So at the end of the day, it just becomes a standard LSTM model, but with these additional slots, these additional memory slots that can impact your representation of the hidden state. Right? So you're no longer looking at some local context, but you're also looking at the memory that's affecting your representation. So that's important. So here's what happens on the Lambda dataset, the one that I've shown you, fairly difficult one. You basically go from 65% to 70% accuracy, right? And if you kind of go from 60% by using standard gated attention mechanism, no, if you're using standard by GRU, if you're using gated attention mechanism, you get about 65.5, about 66. But if you use these additional links, you can go to 70% accuracy, right? Which is still far below what humans can do, but you can substantially improve the performance of the model, and this is the state of the art. Here's another thing. There's another data set called baby data set. You have about 1,000 examples, and you have things like this. Now, this is obviously not, it's a toy data set, it's not a real data set, but it kind of highlights the problem of, like a bunch of people doing stuff, right? And then there's a query that says, where was the apple before the office? So again, you can solve this thing. The answer would be bedroom, right? Because if you kind of like say, well, apple, John picked the apple, and you can figure out John moved to the bedroom, and then John went to the office. John went to the bedroom, and then John went to the office, and then where's the apple? Before, I guess, before the office, then it was in the bedroom, right? So these are easier questions, but still requires a little bit of reasoning, right? Like things for you to understand what's the apple was before the office, you have to understand something about, and you have to find the right sentences, right? So, and again, if you look at this particular task, then if you're actually using the gating piece, right? There's a gating attention. There's certain features that you can add, but it doesn't really help here. Think of gated attention, which is not using coreferences. But if you incorporate coreferences, you can basically solve the task, right? Now, where do coreferences come from? That's given to you, right? Obviously, there are sort of tools. There's effectively the best performing tools is another neural network that predicts what these coreferences are. That's the state of the art right now. So in principle, you can train the model that predicts the coreferences. And given the prediction of the coreferences, it gives you the right answer, right? So you can imagine building these modular blocks of you predicting which links should exist in your model, and then given those links, you augment your model with those links, those skip connections, and then you can get the answer. So summary for far, these linguistic annotations can help guide memory propagation, and it can help you model long-term dependencies better, right? Obviously, this is what I've shown you is specific to language, but it doesn't have to be. You can introduce longer-term dependencies if you have some prior information, right? Obviously, where that prior information is coming from is a challenging task. Now, one thing I want to point out is that the performance drops sharply, significantly, with added noise in linguistic annotations. So if I introduce wrong coreferences, it actually can hurt model performance, right? And you can see why. If I associate, Mary with something else, then the model is going to be more confused. So adding noise is bad. And so the question is, can you jointly train annotations and reading comprehension models? So, can you learn task-specific knowledge? When you say task-specific knowledge, is that my goal is to answer the questions as well as I can. I don't really care about coreferences. That's the linguistic part that linguists care about. I care about answering the questions. So if you can jointly learn what links should exist in the data, then whether these correspond to core references or something else doesn't really matter, right? So there is a lot of work people are trying to figure out. How can we jointly learn the structure of the model, right, the graph of the model, with the goal of being able to answer questions correctly? So that still is an open question. There's been a few papers recently where you can self-attend to everything. You can introduce links with everything to everything, so like a fully connected graph, and try to prune it out, and you get some interesting results in machine translation and such. So it's there. One big missing piece still is the common sense. Here is a document that says Eurythmics were a British music duo consisting of members Annie Lennox and David Stewart. Okay? And the question is, who was the female member of the 1980s pop music duo Eurythmics? The answer would be Annie Lennox. The question is, the question is, if I look at why is this Annie, why is it not David? And the reason why is because you have some common knowledge. You know that Annie is female and David is male, right? That's not given to you in this particular query. Like, I'm sure if I substituted these names by, names coming from some other country, right? Like, you can imagine some random characters and then some other random characters, and I say, who's the female singer? You say, I don't know which one is male, which one is female, right? So there's some common knowledge. And how do you get this common knowledge? We can find some common knowledge, and you basically need data sets to test this aspect as well. A lot of existing data sets and a lot of tasks that I've shown you before doesn't really require this knowledge, right? If I replace Rob Blagojevich, or if I actually replace Barack Obama with some random string of characters, and say president-elect random stream of characters, you would still be able to answer the questions correctly, right? You don't need to know that President-elect Barack Obama was the president and such to answer those questions. But for many other tasks, you actually need this common sense knowledge. So there's a lot of research taking place in that space, right? And people are trying to figure out how to do that. And so in general, how do you incorporate the prior knowledge, right? How can we use coreferences, entity relations, word relations, and to get better representation of the text? And that's, for those of you who are interested in research in general, that's a big open area of research, right? Right now, most of the approaches in reading comprehension are just driven by data because they don't really require you to have common sense knowledge. But there is a lot of work also happening in the space of how can we incorporate some notion coming from Freebase, definition of words and stuff like that to kind of get a little bit better representation of the text. There is also an interesting line of work on search and read for open domain question answering, which is to say, in reading comprehension tasks, you basically make an assumption that the answer is already known, right? I give you a task, think of it like SATs or GREs. I'm sure many of you have taken GREs, right? Like you give me a paragraph and you can answer the questions. You try to answer the questions. And I'm sure many of you have probably figured out that there is a very good strategies of how to answer the questions correctly using alignment and matching and some paraphrasing, right? You can pretty much solve these tasks, maybe even not understanding that much about the overall comprehension of what's in front of you, right? I've been through that myself. But here you're assuming that the passage contains the answer, right? For real question answering, you actually need to search for the passage as well, right? So for example, there is a data set, an interesting data set. For example, a question could be of the form: 7-Eleven stores were temporarily converted to Kiwi e-marks to promote the release of what movie? All right, and so now you have a whole bunch of Wikipedia articles about all kinds of movies, right? So you need to retrieve some information from 20,000 or 100,000 Wikipedia articles, right? So there's a retrieval piece. Once you retrieve, basically a bunch of different information, then you can apply reading comprehension task to really go over these specific documents or these specific sentences in order to be able to answer or produce the correct answer, right? So this is something that you can combine the retrieval and reading comprehension at the same time. So there's a retrieval piece and there's a reading comprehension piece. And these kinds of, for open domain QA is actually very difficult to achieve, because standard practices, what people generally do is people construct predefined relations. If I want to ask you about the movies, then what I can do is I can construct a database of relationships. I can construct, this person is an actor in this movie, and this is a director of this movie, and this movie was released on this date, right? So I can construct a bunch of rules. When the movie was released, who the actor, who the director, and so forth. I can have a very structured set. And then answering questions could be very easy, right? Because if I can just do sort of relational matching and say the actor of this movie, and I just retrieve who the actor is in that movie and give you the answer. And that's commonly how things are done today. You construct a hand-engineered knowledge in a very specific table, and you're just doing table lookups and table matching. The question is, can I go into the open domain question answering, where I ask you arbitrary question in natural language, and you're trying to retrieve the right information from unstructured text, stuff from the web, right, or from Wikipedia. That's a much more challenging task, but at the same time, it's also much more generalizable, right? Okay, so let's finish today. So we're going to have a class on Monday, and on Monday I will go over, maybe give you a little bit of introduction into reinforcement learning, which is another area of research that's been picking up quite substantially in the last few years, and show you some examples of that. But if you're interested in these models, there is a code, there are data sets, so you can download and play with those. Okay.